The following is a production of the University of Minnesota.
Today we have with us Matt Shermer, and he's an independent consultant working on power systems planning and analysis. He has 25 years of experience in the utility industry, including senior positions in engineering, power plant operations, and business development. Matt has worked extensively with the integration of large amounts of variable renewable energy into power systems, including interconnection and delivery, operating impacts, reliability, and market rules. He's a consultant to DOE's National Renewable Energy Lab, to the Minnesota Department of Commerce Division of Energy Resources, and to the Wind of Wires. I attended Matt's presentation last year, and it was good 2 hours, so over to you, Matt.
Great, thank you so much for that introduction. Good afternoon. Thanks so much for inviting me in. So I'm going to talk this afternoon about wind integration, integrating large amounts of renewable energy into the regional power grids and the operating impacts that result from that. I have been working in this area extensively for the last 10, 12 years, worked in a number of studies around the country and upper Midwest in the state of Minnesota. So looking forward to sharing that with you today. It's an area that I've worked in a lot and that I enjoy a lot and I get really excited about. So don't let me just ramble on. I prefer to have questions or get some interaction if possible. So if you have questions as I'm going along, please by all means jump in. So I think most folks know there's been a very rapid increase in utilization of wind power over the past decade with the zero-cost fuel and emission-free power output has great benefits to society and to customers. Utility-scale wind power has really been increasing. It's still relatively new to power system operators, so there's still a lot of work from an operations standpoint of the overall grid and understanding how it works, particularly in large amounts. And understandably, there have been concerns about integrating large amounts of this variable resource into the grid. And so there have been a number of studies over this last 10 years, and so I'll talk about some of the insights from those studies as well as some of the findings. Let's see. I lost it already. Oh, there we go. So I'm going to start off with a little bit of context. I looked over somewhat the agenda you had this year, and I'm not sure how much of this has been covered, but I want to spend a few moments on the front end talking about where we are in wind power, both globally, but in the U.S. and in the upper Midwest. How much do we have, and how much are we likely to have in near-term years? And I also want to talk for context about a couple of recent studies that were done. One by DOE on looking at 20% wind energy, and a very recent one by the National Renewable Energy Lab of 80% renewable energy. Again, just to give some context, both for where we are with wind power, where we're headed, because it's really those amounts, that scale, that's important. So when there was, in the late 90s, there were just a few wind plants on the power system. Nobody really cared, but there's enough on the system now that it really makes a difference and makes an impact in how it's interacting and impacting on the grid. And then I want to spend the bulk of the afternoon talking about really integration of wind power into the grid. How do we deal with both the variability and the uncertainty of wind power? When I say uncertainty, it's not only is wind power, the output from wind plants increasing and decreasing with the wind, but you don't know exactly when it's going to increase and decrease, and so both of those factors are issues and can create some operating impacts for the grid. I want to talk about wind forecasting, capacity value, and spend a little bit of time on grid flexibility and why that's much, much more important as we go forward with more variable renewable generation on the grid. Talk a little bit about wind integration studies, best practices and findings, and then summarize. Again, hopefully we'll have some time for a discussion at the end if you're interested, but feel free to jump in as I'm going along if you have questions. So just starting with context, this just shows kind of the progression of the technology over the last several decades. There's been significant growth and maturation in wind technology, particularly over this last decade. So size, height and rotor diameter, tower design, blade design have all evolved significantly. The modern wind turbines these days are variable speed, pitch regulated, with pretty sophisticated power electronics and technology in them. And even over this last decade, the size has increased significantly. So in 2000, the average wind turbine that was installed in the U.S. was about 1 megawatt in capacity, a little under. And just this last year, the average size was nearly 2 megawatts. In 2011, I think some 40% of wind turbines installed in the U.S. were greater than 2 megawatts. So quite a bit of growth in size. And at that same, over that same 10 years, we've seen a growth in hub height of about 50%, with average hub height now somewhere on the order of 80 meters to the center of the wind turbine above ground. And then the rotor diameter has grown something like 85% over that 10 years, with an average rotor diameter of about 90 meters. So a lot of development, both physically in the wind turbines, but also from a technology and control standpoint. And I think you've covered some of those pieces in your earlier lectures this semester. Just a few numbers for context. These show the 2011 global wind capacity rankings. So both in annual capacity installed in 2011, as well as cumulative capacity. China ranks first in the world, with U.S. second, and you can see then some of the other countries that follow behind. About 250,000 megawatts, about 240 gigawatts of wind power currently interconnected to the grid globally. And if we look at the U.S., this shows annual. The bars show the annual installations in the U.S. And the red line cumulative. So through 2011, about 45,000 megawatts, about 45 gigawatts of wind power installed, and there's been another 4 to 5 installed already this year. So currently about 50 gigawatts or 50,000 megawatts of wind power on the power system in the U.S. You can see this steep increase through 2009. Things did slow down some in 2010 and 11. They picked up this in 2011, and again in 2012 we'll see a pretty strong year, probably about 10 gigawatts of wind power installed this year. A couple reasons for that slowdown. One of the economic turn down hit the wind industry along with other sectors of the economy, but also other factors like low natural gas prices have had some impact as well. This shows wind as a percent of electric consumption. So when you look globally, you range from Denmark, who's currently getting almost 30% of their annual electric energy consumption from wind power. You see U.S. somewhere to the right of midpoint there. Just in 2011, a little under about 3% of our annual electric energy from wind power. So still relatively small, but again, it's in a pretty strong growth mode. In the U.S., I think you're going to hear about wind policy next week from Elizabeth Wilson, Humphrey Institute. But just a little bit on policy. There's 29 states in the U.S., including Minnesota, that have mandatory requirements for renewable energy called Renewable Portfolio Standards. Here in Minnesota, there's a requirement for all utilities to have 25% of their annual electric consumption from wind power by 2025. And there's a little bit tighter requirement on Xcel Energy, the largest utility in the state, for 30% by 2020. And the utilities in Minnesota are well on track to meet those requirements, if not exceed them. This just shows current wind power capacity. This is from American Wind Energy Association, but this is as of October 1 of this year. So there's been about 4.5, 5 gigawatts of wind power installed this year, so about 51,000 megawatts overall currently installed in the U.S. And there's some 39 states that have utility-scale wind power installed. So it's pretty widely distributed, large concentrations in Texas. California was the early leader in wind power in the 80s and 90s. Texas has overtaken it. But you see strong installations in Minnesota. Iowa has a very significant amount installed, has really been pushing that hard. And it's interesting to see the high numbers in Illinois and Indiana. So I'll show you in a minute. Illinois and Indiana have a lower wind resource than we do in Minnesota, Iowa, Dakotas, but they're close to an incredible load, the Chicago Con Ed system, large load, so they're able to economically develop that wind power. With the larger hub heights, larger rotor diameters, they're able to capture that lower wind resource in Illinois and deliver it economically to those load concentrations. So as wind power continues to grow and expand, and as the technology continues to mature, we see this footprint nationally of where it's being installed and developed widening further and further. This just shows a map of annual wind speeds, and just the point here that the strongest wind resource is right through the middle of the country. So again, developable wind resource over most of the U.S., but pretty strong swath right through the middle. And of course, if you really look at that map where you see it from the Dakotas down through Nebraska, Kansas, it's where the lower population densities are, and so it tends to drive a need for more grid build and more transmission to access that wind resource. This is an example of wind capacity factors based on 10-year averages, and this is just an example because you'd have to assume a particular wind turbine or wind power curve from the wind resource. But the point here is that even as you look across the upper Midwest, you see a pretty significant difference in annual capacity factors. Annual capacity factors is a measure of, for a given nameplate rating of a wind turbine or rated capacity, how much annual energy are you getting out of that? So it's a measure of how strong is the wind resource, and it's also a measure of how well is that wind turbine capturing that wind resource. But you see numbers that are varying anywhere from the low to mid 40% in the Dakotas over to the upper 20s, low 30s in Illinois, Indiana. So it's a large capital investment for a wind turbine, and this is an important piece of that economics is how strong is the wind resource and how much are you capturing, how much energy are you able to produce annually for a given site, and it does vary significantly across the upper Midwest. This is a look at the states in the upper Midwest. Again, this is those renewable standard requirements, renewable energy standard requirements, renewable portfolio standard requirements, we call them. The states in yellow are MISO states. So MISO, Midwest Independent System Operator, is the regional grid operator in the upper Midwest. So there's a coordinated grid run over 15 states in the upper Midwest by this organization called MISO. It's a voluntary organization, but the utilities throughout the upper Midwest are members of this, and MISO coordinates the energy markets, day-ahead and real-time markets, transmission planning and build-out, as well as reliability. And so in this footprint, this MISO footprint, upper Midwest, there's currently about 12,500 megawatts of wind operating. If you look at the requirements for wind in this footprint, by 2025, there's a requirement for about 25,000 megawatts. And so they sound like large numbers, and a few of these states, like Minnesota, has a relatively large requirement at 25%. But when you look at the overall footprint, even when these renewable energy standards are fully implemented by 2025, it's only about 11% wind energy on an annual basis. So current wind energy installed in the upper Midwest is on the order of about 5 or 6% of annual wind energy. A little bit higher than that national average of about 3.5%, but just to give you a scale of some numbers. Yes?
I'm curious how MISO regulates this. Is it through the state, or does it in conjunction with the state RPS? Because MISO doesn't necessarily have any regulatory authority over the states.
Yeah, good question. So I was asked to repeat the question for the people that are online, but the question is, what is MISO, the grid operator's regulatory authority? And you're right, they do not have regulatory authority. So MISO is simply the system operator. All of the member utilities turn over control, not ownership, but control of their facilities to MISO for a unified and coordinated dispatch. But policies like this, you're absolutely correct, they're entirely up to the state, and thus you see the variation across the footprint in the different states, different requirements. The challenge for a MISO, because they have to try to figure out how to plan the grid and operate the grid when states have different policies in mind. And this has been a really hot topic lately. FERC, the Federal Energy Regulatory Commission, recently issued an order, it's called Order 1000, that says that the MISOs all across the country, different regions have different operators like this, must take into account public policy when planning their grid. MISO's been ahead on that, so they've been planning around some aggregate of what the states want for some time, but areas east, like there's an area called PJM, which is our ISO to the east, has been reluctant. They want to say, well, we don't do any policy, so all we're going to look at is grid reliability, and that's all we'll plan for. And so the national regulator, FERC, has said MISO and others must take into account public policy, but they have to figure out how to do it on an aggregate basis. So it's a great question, and it's part of our evolving world in power systems planning and development, is that there's a much more explicit role for both state and federal policy in what the engineers are doing, both in developing the grid and in operating it. This shows the progression of wind generating capacity in MISO. Again, this was driven by the individual state renewable energy standards, but you see over the last 5 years really a significant increase in wind capacity in this region, and we expect to see that continuing over the next decade. And just for a little context, so I wanted to talk a little bit about where MISO is with integrating and operating wind. As I said, there's about 12,500 megawatts of wind on the grid in MISO. The record peak, the aggregate, was just set a couple weeks ago, about 9,400 megawatts. So we'll talk a little bit about geographic diversity of wind, but even though there's 12,500 installed, the wind is hitting those different wind plants across this large region at different times. So in aggregate, the peak that the system has seen is a little under 10,000 megawatts. And it's interesting, the middle set of bullets is a set of bullets from MISO staff's report to their board of directors this spring that says that they've gained a lot of experience successfully integrating wind. The variability of wind is being mitigated by geographic diversity. We'll talk about that some in a few moments. MISO has gotten quite good at forecasting wind. We'll talk about how that works and why it's important. Contingency reserves have never been deployed due to a wind output drop. I'll talk a little bit about reserves. Wind does contribute some to resource adequacy or peak requirements in MISO. And I think most importantly, MISO staff and operations folks are saying that they do not anticipate significant operational issues or challenges from this amount of wind. So it's interesting to see as the grid operators get experience, they get more comfort level with this. And this has really just happened in the last couple of years. And then I won't talk too much about market rules today, but the rules themselves are evolving to incorporate wind, and that's an important aspect as well. So before plunging into wind integration and operating impacts, I want to talk about two studies that were done in recent years, again, to provide some context. you just got a sense of where we are with wind power, but where might we be going? How much might we really be looking at? So in 2008, the U.S. Department of Energy did a study of 20% wind energy by 2030. This was a scenario analysis that was done that was done by a team of national lab folks, industry folks, utility folks. And it just, again, it explores some scenarios. It's not a prediction of where we're going, but a look at one scenario of where we might be headed. And a couple of interesting results that came out of the study. One is that it found that the economics of 20% wind energy in this look were roughly a wash. So the increased cost of the wind energy were offset by the savings of fossil fuels. There was a small difference, but not enough to be notable. So it was found in this study by DOE to be pretty affordable type of scenario. Pretty significant CO2 emissions drop. So something like 40% of total carbon CO2 emissions in the U.S. are due to the electric sector. Electric sector plays a pretty important role in CO2 emissions. This scenario with 20% wind energy resulted in about 25% reduction in the electric sector CO2 emissions. So had a pretty big impact in CO2. The overall conclusion of the study is that 20% wind is possible, but also found that it wouldn't happen under a business as usual kind of scenario, that there were policy choices that would need to be made to support 20% wind energy, market transformation, market rules, transmission expansion, and a set of other things. So that was 2008. And let me just talk about where we are in that. So this graph shows trajectory of getting to 20% wind by 2030. So across the x-axis is the year. On the y-axis, on the left is annual capacity installation. So the bars are annual. The yellow bars show actual wind installations in years to date, and the blue bars show the projected trajectory we would need to get to 20% wind energy. So we see that in the yellow bars, we've been running roughly ahead until really this last couple of years. The annual installations needed to get to 20% wind energy. And on a cumulative basis, this red line, we're running ahead as well. But it requires a ramp up to something like 16,000 megawatts a year of wind power, 16 gigawatts. And we really haven't been close to that yet. We had been up around 8 to 10. We dropped down to about 6 or 7 for a couple of years, and we'll probably be back at 10 this year. The dots in the center are just projections from various folks of where we may be over the next couple of years. So we're roughly ahead of this trajectory for 20% wind energy, but it'll really depend pretty heavily on some policy choices over the next couple of years. So I want to shift gears and talk about one other study before we get into grid impacts. Yes?
How much do you think that changed now that all of that?
Yeah, it's a good question. So it's a good question, and it's a complicated question. So it's not just the oil coming out of North Dakota when we're developing a lot more fossil fuels in this country, but all the natural gas that's being developed now. So natural gas is really quite cheap right now. I think that you need to look at those costs and where they are now, but where they're likely to be. We expect those costs to increase gradually over coming years. But wind power costs and solar costs have been coming down pretty significantly in recent years, so I don't have a lot in here about costs, but it's been a pretty significant drop, and so it's hard to tell exactly where that mix will look. When we look at these costs or any of these things, we're making at least a 20 or 30 year investment, so we need to find a way to look over that time period. And the costs need to need to look at life cycle costs. So not only the near-term capital costs, but the operation and maintenance, and also the risk. And that's one of the values of having wind and solar in your portfolio is to mitigate risk for future cost increases. So once you install the wind, you know what that fuel cost is going to be forever, and there's some hedge value to that. So my feeling from what I see even this year is that wind is still competitive. Just this year, we're seeing delivered wind energy in Minnesota being available on the order of 4.5 to 5.5 cents a kilowatt hour, which is pretty competitive with bulk power systems. $2 natural gas right now is about $3 an MMBTU, which is under that 4.5 to 5.5. But in just a few years ago, we had natural gas at $8 to $10 an MMBTU. I think these reserves of oil in Dakotas as well as natural gas out east are very real and are going to go on for some time. But I'd expect natural gas to come up at least into the $5 to $6 range. So I think in life cycle costs they'll still be competitive, but it's a good question because these figures are shifting very much. Yes?
I think the other answer to that is we don't use oil to produce electricity, so generally, and on the U.S. market, correct? So unless there's a deep transition to electric vehicles and the fuel to power vehicles shifts that way, a bunch of oil entering the United States doesn't really shift the cost of energy that much.
Yeah, it's a good point. So the comment was that we don't use oil to produce electricity, which is great. There is some linkage in these markets, oil and natural gas markets, and they are to a certain extent global markets, but it's part of this overall picture. The wild card in this piece is policy on carbon, and where will that go both nationally and internationally, which could have a big impact in those costs. So I want to talk just briefly about this 80% renewable report that came out, and then jump into the main subject of operating impact. So this came out just in June of this year, National Renewable Energy Lab and a broad team of other national labs. And the motivation of this was really to look at a future with a fuel mix of low carbon, low air pollutant, low fuel use, and to what extent could you have renewable energy in that mix. So these just show current mixes. Currently, current here is 2010, which is when this main analysis was done, even though the study just came out this year. There's about 10% renewable energy. That includes about 6% hydropower. So in 2010, there was about 2.5% wind energy. Again, that's grown to nearly 4% this year. And part of the study just identified how abundant these resources are. So identified about 10,000 gigawatts of wind power in the U.S. When we look at these scenarios, this 80% scenario has about 30% wind energy in the mix, and it's using something like 300 or 400 gigawatts. So out of 10,000 available to develop to get to this high renewables future, it's using just a tiny fraction of that. And similarly on the solar PV, a very large amount of resource. And one of the things to note on these maps is that when you look at the mix of renewable energies, they're really available throughout the country. And so that was one of the findings in this study, is that not only was this kind of a high renewables mix technically possible through the analysis, but that it would drive not just development in traditional high renewable energy regions like the Midwest, but throughout the country as well. This shows some of the supply mixes going from on the left to a baseline current mix to the right, all the way up to 90% renewable energy. And again, this includes hydro and biomass, as well as wind and photovoltaics. It also has concentrating solar power, which is more common in the Southwest. And the focus of this analysis was on the 80% renewable energy. Part of the results here was, again, significant carbon reductions through such a scenario, as well as significant water usage. So we don't think about that much, but we're starting to see restrictions, particularly with weather extremes in in water usage and consumption. Electric power production is a high consumer of water. It's been a limited resource in the southwest part of the country for some time. We saw just this summer, for the first time, we saw a couple of large coal-fired power plants needing to shut down because they're, with drought conditions, there wasn't enough water for cooling of that power plant from the river. The water was too low. And so at the hottest time of the year, it had to close down because of water availability. So we'll hear more and more about that, about electricity usage and water as well as we go forward. Costs do increase under this scenario. The study found that they were competitive with other types of clean energy scenarios. Yes?
The two reports and models that we just spoke about,
Yeah.
what is the rate of increase in the energy consumption or energy generation from now to 2030 or 2000?
Yeah, that's a great question. So the question was, what are the assumptions for electricity consumption growth? So when you look historically, in the country and in this region, we've seen 2 to 3% annual growth in electric energy consumption. We saw a big setback from 2008 to 2010, 11 with the economy. But as you know, certainly we haven't come out of that recession yet, but we've started to. And what utilities are seeing, particularly in the Midwest, but throughout the country, is that electric energy consumption is not picking back up. And so it's, we're starting to see a decoupling from the economy, and we're starting to see a greater rate of efficiency throughout the sectors. Utilities here in the state, Xcel Energy is projecting for the next 20 years annual growth of much under 1%, perhaps flat growth. And so in this study, their main analysis looked at a low growth scenario. So looked at close to flat electric energy consumption through 2050 through large amounts of energy efficiency. And they even incorporated the assumption that over that time frame, so again, this analysis is out to 2050, that there would be a sizable increase in electric vehicles, electrification of the transportation system. So it's really looking at a fairly flat growth. They did run what they call a high growth scenario, and in this analysis, that was at about 1% annual growth rate. So many sectors, many analysts are seeing really flattening electric consumption going forward, seeing a lot of opportunities there. Costs do increase. They found it was similar to other clean energy scenarios that were run. So Environmental Protection Agency and Energy Information Administration, EIA, have run scenarios that include large amounts of nuclear or some types of clean coal technologies that are clean scenarios. They found this one is similar to that. There was an increase of somewhere on the order of $10 to $20 per megawatt hour by 2030. So, you know, about a penny to 2 cents a kilowatt hour increase. So again, some increase, but in line with what other studies have found. And just overall in the study, I think the interesting and key finding is that renewable electricity generation from technologies that are commercially available today, so not assuming huge new developments in technologies, in combination with a more flexible electric grid, and I'll talk a little bit about that here shortly, that it was possible to get 80% of total U.S. electric generation from renewables in 2050. Again, you need to increase the flexibility of the power system to deal with that. So in this 80%, somewhere on the order of about 45% was variable, wind and solar. So it wasn't all variable, but it was a pretty good chunk, 45%, found that the power system could technically balance that amount going forward. So with that context, I want to talk a little bit about integration, wind integration, and the challenges associated with wind integration. So as I said, it's really, it's really a question of keeping the power system reliable, maintaining we need to have a real-time balance between load and generation within some statistical limits. So there's reliability standards that are set NERC, the National Electric Reliability Corporation, sets standards for reliability and sets the statistical limits for that balance. Output of wind plants can't be controlled or scheduled with a high degree of accuracy. They can be forecast. I'll talk about those accuracies, but not perfectly. And wind plants are now large enough to have a measurable impact, so it's important to take a look at these things. A couple of key characteristics, as we've talked about, it's variable. It also tends to be remote from load, so some distance by transmission. And even with the amount that we have on now, it's still relatively new. So there have been literally decades and decades and decades of experience with nuclear and coal plants and gas plants. And there have been a few years of experience in this country with operating with large amounts of wind. And so it's important to recognize those characteristics and to account for them fairly. I mentioned this earlier, but it's not just the variability of wind power, the ramping up and down of the output with the ramping up and down of the wind, changes in the weather, but it's the uncertainty that's important. So not knowing exactly when it's going to come up and down can have some impact on scheduling, resources, planning, and operating the system. It's important to keep in mind that variability and uncertainty are not unique to wind power. So these are inherent characteristics in our power system. The load, the consumption is varying all the time. We're changing what we're using in our homes, turning lights on and off. Factories are turning motors and switches on and off. It's varying quite a bit. We talked earlier about MISO, the regional grid, which covers some 15 states, but we have interchange with adjacent grids. And so that's a source of variability on our power system, is that import-export that's changing all the time in response to markets. We have conventional power plants, fossil plants, that while they can be dispatched and dispatched with some accuracy, they do have some deviation from instructions. So you have some variation in plants being not quite where they're supposed to be. And so the power system operators have been dealing with that kind of variability always in the power system. Wind power adds some variability to it, and it's that overall net of those effects that's important to balance. So it's looking at how wind fits into that overall equation that's important. This just shows a pretty simple curve of wind output here in the upper Midwest. This is 24 hours in August, but a couple of key things to really keep in mind is that, generally here in the Midwest, and I think people are aware of this, it's windier in the winter than in the summer. So our best wind resources in the Midwest are expected with these strong pressure gradients of the winter season or the transition spring and fall. So again, we tend to get a stronger wind resource in the winter. We also have a significant diurnal characteristic. So we tend to have stronger winds at night than during the day. And when you think about it, that's really out of sync of our load patterns, our consumption patterns. We tend to have higher electric consumption during the day than at night, and in the summer than winter. So that's an important factor to look at, is how wind as an energy resource actually contributes. Yes?
Do you think time of use pricing has the possibility to help even that out? Shift load from the daytime towards the nighttime?
Yeah, let me get to that, because I think we don't want to. One of the things we want to avoid here is trying to make this curve look like a central power plant, because we don't need to. So I'll talk a little bit about the overall system. There is some benefit when you look at that whole system in both rules that could shift daytime load to night, but also some emerging energy storage technologies. But I guess just to do a quick response, at the levels of wind power we have now and in the near term, it's not really a factor, and it won't become a factor until we get much higher penetrations. So this is part of wind's natural characteristics. This is just a graph that shows a wind power plant during a high wind event, and this upper graph is a 24-hour time period, And the lower graph is a 3-hour expansion of the middle section of the upper graph. And so what you see in the light blue in the background is the wind speed coming up and then coming back down. And the 4 lower lines are individual strings of wind turbines in a wind plant. They have somewhere on the order of 15 to 30 wind turbines. And the line up above is the aggregate of those wind turbines, power output. So a wind turbine, as the wind increases, will continue to increase its power output until it gets to a certain point. By design, wind turbines are designed with a high wind speed cutout. It's at about 25 meters per second wind speed, typically, about 55 miles per hour, where the wind turbine is designed to shut down and protect itself, turn into the wind, feather its blades. It's interesting, there were wind plants that were directly in the line of Hurricane Sandy this past week that were not damaged, specifically because they have this characteristic. But it's interesting to look at because when we talk about variability, it's some of the most significant variability you could have is when you have a high wind speed cutout on a wind turbine. You think of the power just dropping off. What this curve shows that even for a single wind plant, that front of weather hits the turbines throughout the wind plant at different time periods. And in aggregate, you never lose that whole wind turbine plant output. That geographic diversity of individual wind turbines within a single wind plant is enough that you get some smoothing. And I'll show some pictures of how this diversity becomes more important as you look over a region. So another look at this is just a generalized view of aggregation. The graph on the left is variability. Just qualitatively, you see variability of a single wind turbine, and then 30 wind turbines, 150, and then the whole wind plant. You gradually get smoothing of that power output as you go out. And this phenomenon has been generalized of geographic diversity. This is a set of factors, of correlation factors. So how correlated is the output from different wind turbines is a factor of the distance between those. So on the x-axis, you see distance up to 600 kilometers. Some 350 miles apart, and then you see curves of time. So the greater distance you have, the less correlation you have in the output, and the shorter the time period. So this is contributing to that smoothing of regional power output. And just one more look at this. This is a very specific curve from the Midwest ISO. And again, you see the states on the map there that are part of our regional power grid. And you see that from east to west and north to south, we're spanning almost 1,000 miles in this grid that's operated and coordinated together. And we have wind plants all across that 1,000 miles. And what these curves show is correlation as you move. The green is an east to west line, and the blue is a north to south line. And it's just, they're a little bit different because of the way our typical wind patterns move across the Midwest. But they show that as you get increasing distance, you're less correlated, which means that there's an offset in those power curves. And when you aggregate them together for the power system, you see an overall smoothing. So again, as distance increases, the correlation drops, and as time increases, the correlation increases. So over short time periods, all wind plants are uncorrelated. And so when you think about variability, what we'll see as we talk about the different time periods that are important, integrating wind power gets to be more of an issue of a load following or balancing issue, a tens of minutes to hours issue, not a seconds or minutes issue or a short-term variability issue, but a tens of minutes to hours. And it's a much different kind of problem when you shift it into that time frame. This just shows some overall general numbers on wind forecasting accuracy. So wind forecasting has become really important for power systems that have a lot of wind power on them. And it's important both in the day-ahead time frame when you're planning what power plants you need for the next day, but also in the hour ahead when you're actually operating and trying to figure out if you have enough generation to move. And I'll just draw your attention to the lower right hand here. When you look at day-ahead hourly capacity, the error in forecasting is on the order of 6 to 8%. And these figures are actually a year or two old. I don't know, maybe Mark Ahlstrom gave you a little bit different numbers. He was in a few weeks ago. He's the best. So whatever Mark said is true. These numbers are a little generalized, but I think they were on the same magnitude. So, an error of 6 to 8% on hour ahead, and I'm sorry, I'm switching here. This is on day ahead, 6 to 8%. Hour ahead, 3 to 6%. So a large amount of the wind power, both hour ahead and day ahead, can be forecasted with a pretty good accuracy. Just for contrast, when you look at this, there's load forecast error. So that's the other piece. We're trying to forecast wind, schedule conventional dispatchable generation, and have that combined meet a load forecast, both day ahead and hour ahead. And typically on a day-ahead load forecast error is about 2%. It varies kind of in the 1 to 3% range. So the accuracy of forecasting on a percentage basis is more accurate for load, but of course it's a much larger amount that percentage is applied to. So the absolute amount of load forecast error in megawatts or gigawatts is larger than wind, but on a percentage basis, the load forecasting is a little bit better. But still, the other pieces that are important here is it's much easier to forecast regionally than for individual wind plants. It's much more accurate on an aggregated system-wide basis. So the grid operator is looking at their regional aggregate grid integration. And again, in day ahead, they can predict, on order of 95% accuracy, 6% or so forecast error for day ahead. An important piece of that integration. I lost it here. There we go. One other look at wind variability. We talked about high-speed wind cutout, but we also have extreme wind events the other direction, where wind just drops off. We had an event in Texas, which their grid operator is called ERCOT, but it's basically the Texas grid. And this was about 5 years ago. And on the left, we see curves for individual wind turbines. And so the line in red is the most severe drop of an individual wind turbine. But on the right, we see the aggregate of all the wind that was on that grid. And the important piece to see is that while on the sharp edge of this weather front moving through Texas, we saw extreme drop-offs in wind, and some wind plants dropped off quickly. When you looked at the whole event, there's a big chunk of power that came off. It was about 1,500 megawatts, but it came off over a 2-hour period, which is really important, 2-hour period, and it was forecastable. And so it's something that the operator can deal with and respond and plan with. And so as a result of experiences like this and analysis that's been done, we don't have any grid operators that are considering wind as a contingency event. A contingency is we have contingency reserves to plan for the sudden loss of an element in a power plant. So you have to plan for loss of your largest power plant suddenly, or a large transmission line. But wind is kind of a different beast. It's not considered a contingency event, except the exception is for electrical events. So if you have a transmission line, which is serving a single wind plant or serving a couple of wind plants, if you lose that electrical line, you still have a contingency event. You'll lose that output suddenly, as with any generation source. But weather-driven, wind-related events are not considered contingency events. They're slower than that and impact the system differently. So I have a couple of figures that just talk about how this variability of wind overlays with time periods that are important on the power system. And this figure and the next both kind of address this. But we see on the left, on the upper left, the time frame of individual wind turbines. And then as we move across on the upper left, individual wind farms or plants, and then regional wind plants, and then seasonal winds. And we see on the bottom axis that the variations change from tens of seconds and minutes all the way up to days and weeks and on the far right, years. So all of these time periods are important in the planning system, and we need to look at how the wind varies differently in those. This is another look at that same phenomena, but we just see we see variations from the very fast seconds at the bottom, frequency or regulation, what's called automatic generation control, which is balancing in the seconds time frame, and moving up through load following, tens of minutes to hours. Unit commitment is day-ahead scheduling of power plants, and then resource adequacy is over multiple years. Do we have enough generation capacity installed in the system? Do we have enough capacity to meet the overall peak load? And as we're discussing, and we'll see more, the impacts of wind come in more into a load following, balancing kind of situation. So to talk a little bit about wind integration studies, I want to make some differentiation between interconnection and integration. So, and they're a little bit of a different, let's see if I get that the right place, a little bit of a different set of questions. So when we talk about interconnecting wind power, we're really talking about technical questions that are centered largely on the transmission network, thermal voltage issues, transfer limits, stability, security. And that's an important area, but it's not an area that I'm going to spend a lot of time on today. I'm really looking more at integration, which is assessing the impact of wind power on operations, interaction with all the generators and loads on the system. Transmission does play a role, but it's looking at that overall operating impacts area. So as I said, there's been a lot of study work done in this area internationally and nationally over the last decade. There's been a couple of really focused studies done here in Minnesota led by the Public Utilities Commission with Minnesota Utilities. There was a large one in 2006 that led to our renewable energy standard, technical analysis and integration of wind in issues. So these studies typically are focused on quantifying physical impacts of wind generation, dividing impacts by time scale, so those scales we talked about, regulation, load following, unit commitment, and planning. And then analyzing wind in the context of the entire system. So that's the key piece here, is figuring out what is the net impact of wind rather than isolating wind on its own. It's important in these studies to capture system characteristics through modeling, as well as wind generation characteristics. So these studies can be pretty data intensive, require a large amount of detailed information about system load and generators, but also some pretty detailed models of the wind resource. And they really examine, again, the combination of wind and load and other things that are moving around. It's important to incorporate wind forecasting and wind forecast errors. So that's a key piece of the impacts, is how much is that error in wind forecast, and what does that mean? How does that have impacts on your operation and on the cost of your operation? We talked already about these time scales. Regulation is seconds to minutes. It's the cycle of what's called AGC, or automatic generation control, that keeps that real-time balance and keeps the frequency at 60 hertz. Load following, tens of minutes to a few hours. Scheduling and commitment is that day-ahead time frame of planning generation for the next day. And then capacity value. How much does wind generation, while it's primarily an energy resource, to what degree does it contribute to long-term reliability? To what degree can you technically and analytically count on it to meet peak demand? There's some portion of wind power which you can rightfully, through calculation, attribute to capacity value, and so that's an important time frame as well. Operating reserves are really where we see this wind integration impact coming to play. So this is a NERC definition, a National Electric Reliability Corporation definition. Operating reserves are that capability above firm system demand required to provide regulation, load forecast error, in this case load and wind forecast error, combined forecast error, equipment forced and scheduled outage, local protection. So we carry operating reserves on the system to ensure reliability. So we make sure that we carry a generation above and beyond what is actually needed to meet peak demand in order to meet these categories. In the U.S., we combine spinning and supplemental reserves into contingency reserves. These reserves, contingency reserves, are required to meet the single largest outage. In the upper Midwest, it's not an outage of a power plant, but our largest outage is actually a transmission outage. And it's the tie line from Canada. There's a 500 kV line that when we lose that, we lose 1,500 megawatts. And so we carry contingency reserves above and beyond what's needed for peak demand to be able to deal with that outage if that were to occur. And these reserves, again, are a mix of spin and non-spin. Spin means that the generator is essentially hot. It's synchronized to the grid and ready to go instantly. Non-spin takes some time, typically 10 minutes or so to start up. And our reserves are differentiated by the type of event. So some reserves are used in normal operation, like regulating reserves. Those are used for these fast variations, these seconds, minutes variations, automatic generation control. You need to keep some generation in reserve to be able to move up and down rapidly and automatically to regulate the system. And they're differentiated as well by time scale response, seconds, minutes, or hours. And so when we're looking at variability of wind power and the net impact on the power system, we're often looking ultimately at how does it affect these reserves, and then what is the cost of that effect? What is the cost of integrating that wind power due to the impact on reserves? You see this question all the time, does wind power need backup generation? So total load must be met by a combination of generation. And we're not backing up any individual generator on the system. So any large conventional plant, a large coal plant has a high degree of reliability, but it's not perfect. It has a forced outage rate typically on the order of 5-6%, depending on age. It could be older, it could be larger than that. You can lose that plant suddenly, but we don't back up those individual plants. We rely on the whole system and look at the reliability of the whole system. And wind power fits into that overall system. So it does not require backup. Analysis has shown that. But it does have some incremental impact on reserves. It does require a small amount of increased reserves, as do other generators on the system. And then we can look at operating impacts in these other areas: regulation, load following, scheduling, commitment, as well as market operations. And I'm going to talk a little bit about each one of those categories in a little bit more detail. So when we look at the operation of the power system, we can do a decomposition of loads into these time frames. The green, so this is over time, the electric power consumption. This is over a single month. Each one of these peaks is a day, and so that large green base is base load generation, and then the blue is load following, and then that small line on top is that regulation that's needing to vary very quickly to keep things in balance. And there's a lot of contrast between regulation and load following and what characteristics we need from resources to do that. Regulation tends to be random and uncorrelated. It's not really a consumer of energy. It's got positive and negative deviations to keep the frequency at 60 hertz. And so we want to look at impacts on both of these. So we look at wind power in these wind integration studies. We look at its impact on each of these categories and each of these time frames. And to calculate regulation impact, we use actual high-frequency data, load data, as well as actual wind data, and look at how those characteristics combine. The general findings have been that even with large amounts of wind power, this slide says 15%, but studies have been looking up at 25, 30 more percent wind power. Very small impact on regulation. And the reason for that, again, is what we talked about previously about geographic diversity. So in that regulation time frame of the seconds and minutes, wind power that's distributed over hundreds of miles is aggregating and smoothing itself in that regulation time frame. So we don't see an impact on regulating reserves. The other piece is that the load variations in that same time frame, all of us turning our lights on and off, or factories turning motors or machines on and off, that kind of variation in the fast time frame is uncorrelated with the wind variations. You think about it, they're different systems, different characteristics. So as you combine those together, you get a smoothing as well. This is important because when you look at the operating reserves, this regulation reserve tends to be the more expensive reserve on the system. So if we were impacting this, we would see cost impacts of some significance. But the finding is very minimal impacts from integrating large amounts of wind in regulation. And as I noted from my earlier slide, our grid operator confirms that they're just not seeing much impact in this time frame. Talk a little bit, move on to the load following time frame. It's interesting to look at what we call the balancing area, the region. So historically, we had individual utilities. They were called control areas, and now the terminology we now use is balancing authorities, had to meet the NERC reliability standards individual utility basis. But we've since functionally aggregated. So not only is MISO, the independent system operator, planning and dispatching the system across the upper Midwest, but the reliability standards that must be met are being functionally aggregated. And independent of wind or renewables, it's just a recognition of this aggregation benefit that reserve requirements go down when you aggregate more load over a larger area. And so that's a big benefit to the power system as a whole, but also for integrating wind. Load following, again, based on actual load data, wind data from the same period, adding wind in to look at existing variability. And in those same types of models, we're looking at unit commitment. So typically we're running production cost models that simulate the economic, security-constrained economic dispatch of the system and the commitment of resources, and stepping those models through multiple years and layering the wind in over top of it. And then day-ahead issues. Part of that modeling and process has really shown the value of forecasting and the importance of scheduling wind in the day ahead. So when we got up to thousands of megawatts, we're now at almost 13,000 megawatts of wind in the upper Midwest. Once we got to thousands of megawatts, it became really clear that it was important to incorporate through the day-ahead wind forecast that wind in the scheduling for the next day, to not have it just show up, because that could be a pretty significant impact. But again, the forecasts have been relatively good, and so that scheduling has integrated well. And towards the end here today, I'm going to talk about some of the overall results and findings of these studies in aggregate. But again, most of the costs, and the costs have been shown to be relatively small for integrating wind, on the order of $5 to $10 per megawatt hour of wind energy, about half a cent to a cent maximum, to handle these additional operating reserves. It's largely come from the balancing and load following time frame and some unit commitment and scheduling.
Do you see any uniform switch or in the costs when you're comparing regulated and deregulated electricity markets?
Not so much regulated or deregulated, but what you do see is a big difference between regions that have an ISO that's running a fast energy market, 5 to 15 minutes, versus regions that don't have an ISO and are doing hourly scheduling. So that's a little different than regulated or deregulated, where in a deregulated market, people can go anywhere to buy their retail energy. But so that's not as much an issue of integration as the time frame of the energy market. So places that have a MISO or a market like that, which is Midwest, Northeast, and California, in MISO, every 5 minutes, they're looking at the system, rebalancing it, rescheduling, redispatching it. So to the extent that the wind has moved during that time period, you're redispatching everything else. In the Northwest and Southeast, they don't have those fast energy markets. And so they're only looking at it hourly. And if you're looking at hourly chunks and you have a bunch of your generation that's variable, you can have quite a deviation in that time. And so that's found to be a huge benefit, is these fast energy markets like the ISOs. I want to talk for a moment about capacity value. I've already mentioned it a few times today, but wind is primarily an energy resource, but as I said, it does contribute some to this capacity value, long-term resource adequacy. And the measure that has become the industry standard is called ELCC, effective load carrying capability. And it's done within a broader reliability metric called LOLE, loss of load expectation. So LOLE or LOLP, loss of load probability, is a reliability metric that looks at the overall power system, all generators, and it's a standard metric that we use, and looks at reliability of generators in combination with each other, and looks at how those compare to load through the year, and make sure that you meet a certain reliability standard in matching those throughout the year. And so in this country, we use a standard of 1 day in 10 for reliability. We have outages of no more than 1 day in 10. And these LOLE models are calibrated to that. And so even though wind is an energy resource, it's variable. With sufficient wind data, multiple years of data, you can fit this, and it has been shown to be analytically correct to fit it into these standard reliability models. And through the ELCC can look at capacity valuation. Throughout the country, this is a NERC slide, and this is actually a few years old. Again, National Electric Reliability Corporation, which sets our reliability standards, has found capacity value to vary from 10 to 20, and actually currently it's ranging up to 30% of nameplate. So it's saying that it's a fraction of that wind plant, which again can be attributed to long-term resource adequacy. And it varies around the country because it's pretty dependent on both the wind characteristic and the load characteristic in a particular part of the country. So when we look at this effective load carrying capability and we look at wind capacity value, what we're really saying is on a rigorous analytical basis, what is the history, multi-year history of wind being available at the high-risk hours? And in the Midwest, where summer peaking, so high-risk hours typically means a hot summer afternoon, those hours 2 to 4 o'clock, 2 to 5 o'clock, where it's peak load. But the importance of this reliability metric is it looks throughout the year. And so in spring or fall, when large conventional generators are taken off for maintenance, you can have some high-risk hours. You can have some high-risk hours around that peak summer hour. So it's more than just meeting the one peak hour load. And again, it's a metric that's developed for all generation that we fit wind in. It's not a special metric for wind. And so it depends on the wind resource in a particular part of a country, of how it matches in. In the Midwest ISO, they run the effective load carrying capability. This is just, there's a slide in there with some different metrics that are used as approximations. But we run this metric, and the Midwest ISO, MISO, runs this metric annually as part of their reliability assessment. And for 2012, they set wind capacity value based on calculation at 14.7% of nameplate, so about 15%. So if you have a 100 megawatt wind plant, you can get capacity value, credit, and payment for 15 megawatts of long-term resource need. And it's saying that that's a rough measure of the portion of that plant that historically and statistically has been available at those high-risk hours. This shifts a little bit with wind resources, as I said, and one of the interesting things about the development of offshore wind, we're starting to see more proposals for offshore wind off the East Coast, is that the characteristic of wind that I talked about earlier is quite a bit different over water. And so over the ocean, and frankly over the Great Lakes as well, because of the difference in surface roughness and the way that the weather patterns develop, you see a higher wind resource in the afternoon than at night. And so when you run these reliability metrics on offshore wind, you come up with capacity values of somewhere around 40 or 45% of nameplate. So it's important to look at the particular resource, and it's an added value of this concept of developing offshore wind. This graph just shows a kind of the continuum of stability, balancing adequacy across the bottom. So really different looks at this wind integration challenge. The underlying objective of all three of these, stability, balancing, adequacy, is all to maintain balance of the power system, but in different time frames. And so again, we're really focused on this middle one, balancing of tens of minutes to hours or even days. And when we look at this, again, we're really interested in net load variability and uncertainty. So net of variable wind generation and load, and what is that resultant, and how does that need to be balanced? And so it's this net load that's important, and it's really driving when you look at where we are with wind generation, and more importantly, where we're headed as you get up towards higher penetrations of wind on a system, on a regional grid, 15, 20%, 30% plus. We really anticipate a need for greater power system flexibility. And when we talk about power system flexibility, we're really talking about the ability to increase or decrease supply or demand in response to fluctuations in either supply or demand, and fluctuations whether they're expected and planned or whether they're unexpected, whether they're contingency events. And we need it in various time frames. We need the ability to ramp up and down over time. We were just talking a moment ago about institutional flexibility. So there's a certain amount of flexibility that's inherent in how the power operation rules are structured, whether there's fast energy markets, redispatching the system every 5 minutes as we have in the Midwest, or whether it's hourly scheduling in the Northwest. In the Northwest, there's a lot of wind power now in the Bonneville Power Administration system, Oregon, Washington, and the hourly scheduling has become a large problem. So they're looking at easing their wind integration by developing sub-hourly scheduling protocols. And there are other sources of flexibility as we get to higher penetration. So this is a flexibility supply curve, very simple, put together by National Renewable Energy Lab, but demonstrates that when we look at power system flexibility, we're looking at both supply and demand side. So typically when we think about flexibility, we think about generators. We think about natural gas combustion turbines. Those are very flexible. You can start them up, ramp them up or down. And those are important, But there are other sources of flexibility, other sources of flexible generation, and importantly, there's demand side flexibility. So we're starting to see more and more use of what's called demand response, of having customers, either large individual customers or aggregate customers, participate in the market and be able to bid in reductions in their demand in a similar way that people bid in generation to be able to balance the system out. So, and this has been particularly enabled by new technologies, power electronics, monitoring and controls and communications, as well as technologies of the grid to be able to link those two together. So yeah, we were talking on the break a little bit about smart grid development and of an intelligent grid and a grid that has a better communication system and better control system. So both demand response and smart grids can support deployment of variable energy resources, variable generation, and these will become more and more important as we move forward and get greater penetrations of variable generation on the system. You hear a lot about storage these days, and we'll hear more about storage as we go forward. You know, I think you folks know well that electricity is kind of the ultimate real-time product. We don't have a good way in volume to store electricity. We have some pumped hydro storage where water is pumped up to a reservoir at a higher elevation at night and released down through a turbine during the day. There's been some talk about development of compressed air energy storage, where you compress air in caverns underground and then can release that through turbines during the day. But there are other technologies of storage that are under development, currently relatively expensive technologies. And the important thing to realize here, we talked towards the beginning of the discussion about moving daytime demand to night. And so storage is one way to do that, in addition to some incentives through tariffs or rates. But it's expensive, and so we want to make sure that we're looking at it in the right context. And when we look at the whole body of literature that's been done on wind integration studies, even up to 30% wind energy penetrations, we haven't seen a technical requirement for storage. That is, the power systems have been able to handle and balance that wind power. But cost-effective storage and storage technologies are developing and becoming more cost-effective, can be valuable as a system resource. So when we're thinking about storage, we want to think of it from a whole system perspective, not from the perspective of an individual resource like wind generation. And the assessments that are happening now with storage are really looking more at a multiple set of benefits, multiple set of revenue streams. So historically, when we look at storage, for example, the pumped hydro storage systems that we have, typically those were justified just on what's called an energy arbitrage basis, just looking at moving, storing low-cost electricity at night and selling that electricity during the day, just arbitraging between those 2 points in time. But we now see that we can see that there's a whole suite of benefits that you could get from storage, including ancillary services. Ancillary services are this set of services that are needed to support the operation of the grid. So things like frequency regulation, voltage support, storage could strategically located help with those. Storage could provide capacity value. Could provide transmission and distribution support. So we're in the early stages of development of cost-effective storage technologies, but we see over the coming decade or two that this will have a growing role in the system, and will be part of a flexible system as well. So I want to talk. I have a couple of slides about some work that was done by IEA, the International Energy Agency. And it's pretty interesting looking at this balancing challenge, looking at integration of large amounts of variable renewable generation, and how do you look at the flexibility of a power system in dealing with that. So as as we look at the components here, this is just showing the main factors that need to be taken into account when assessing flexibility. And on the left of this, we see needs of flexibility. So demand, variability and uncertainty, and variable renewables. Those two together, as we've been talking about, make up net load. And we also have contingencies, things like sudden outages of power plants or transmission. Those are a combined need for flexibility. And on the right, we see sources of flexible resources. So certainly dispatchable power plants like natural gas combustion turbines or combined cycle plants are sources of flexibility. But also demand-side management we were just talking about, energy storage, but also interconnection, both within a grid and to neighboring grids, is a source of flexibility. So that's kind of a relatively new concept, is to think of the grid itself, the actual transmission, and the robustness of that transmission as a source of flexibility. And when we see grids that can handle large amounts of variable generation, it's largely because, or a key component of that is their ability to aggregate both within their footprint, but with neighbors adjacent to their footprint. So IEA has, again, International Energy Agency, has developed a relatively simple flexibility assessment tool that first, looks across the top at these four categories of flexible resources and looks at assessing the max technical capability. So in the resources, what's physically there as far as flexibility, and then in the second step here captures the extent to which certain attributes of the power system will constrain the availability of that flexibility. So things like grid strength, operating or market rules, and the use of forecasting. Those are all things that could either enable the accessing system flexibility or constrain that flexibility. The third step is, again, looking at this net load. What is the need of flexibility, variable generation, variable load, and then combining those together to get some assessment of relative amounts of variable generation that could be handled. So there's a lot on this chart. I just want to hit a couple of high points here. So this is comparing, again, in a very simple basis, flexibility of some power grids around the world. And across the top, we see some basic attributes of this system. So how large a geography, I'm reading from left to right on the top, is that grid covering area? How large does it have where it could aggregate loads and variable generation? What is the interconnection with neighbors? What is the strength of that? How many markets are there in that grid, and how collaborative are they with each other? What is actually the geographic spread of the renewable energy resources? Are they spread throughout that footprint, or are they all in a single spot where they're all going to react to the same weather at the same time? What's the flexibility of dispatchable generation? And then what's the grid strength within that footprint? So these are some of those key attributes that affect flexibility, but also the ability to integrate variable generation like wind power. And I just highlight Denmark, which is about halfway down the page, and then Japan, which are a couple lines further below. Arguably both island systems, but some notable differences here. So Denmark has a single market, but they have a high degree of collaboration with markets around them. And they have very strong interconnections to their neighbors. So Denmark's system has a very strong interconnections to Norway to the north and to the European grid to the south. And they have a very stiff grid within Denmark. And in contrast, Japan is truly an island system. There is nobody to interconnect to of neighbors. They have 10 separate markets within that small island of Japan, 10 utilities that really aren't cooperating with each other at all. And we saw the problems of that when the tsunami hit. a year and a half ago now. That was an issue in recovery and in sharing of resources, that those independent grids weren't well interconnected or collaborated, and they have a relatively weak grid within their system. And so when you look at those two systems going forward, you see Denmark and Japan falling on the bookends here, where Denmark is positioned to integrate large percentages of renewable energy because of those flexibility attributes. And Japan, in a relative sense, again, this is just a high-level course assessment, relatively less. And so it just gives you a sense of those varying components, both physical and market rules, that are important in looking at both flexibility, but the ability to integrate renewables. So overall, key factors that influence wind integration impacts and costs. Certainly the level of wind penetration is important. You know, whether you have 10% wind energy or 30% is going to impact the cost of that integration. Balancing area size, so the area over which you're trying to meet those reliability statistics and balance the system in a seconds, minutes, tens of minutes, hours time frame is important, as well as the conventional generation within that mix, within that balancing area, and how much load aggregation benefit you get from that balancing area size. Wind resource geographic diversity is important. Time period for scheduling and dispatch we've talked about. So is that system being both scheduled and dispatched in a relatively short time frame, 5, 10 minutes, 15 minutes at the most, or is it on an older, coarser system, hourly scheduling, like some parts of the country? Market-based or self-provided ancillary services, so these additional services that are needed to support the grid, are there markets available for those? Are reserves available through markets? Are there liquid markets to provide those, or are those more ad hoc? And then size of interconnected electricity markets. I wanted to show a couple of graphs of a wind integration study cost results. So over the last 5 years, there's been a couple dozen studies done that take a detailed analytical look at these wind integration issues I've been talking about. And across the x-axis here, we see wind penetration. This is on a capacity basis, but you see ranging all the way up to 60%. Most of these studies in the range of 10 to 30% wind penetration capacity basis. And on the x-axis, you see integration costs, and this is in dollars per megawatt hour of wind. So when you see an upper bound around $10 per megawatt hour, that's something like a penny a kilowatt hour. And it's really the cost of the additional reserves needed for the variability and uncertainty of the wind generation. And what I've highlighted here is those studies that were done in fast energy markets. So you see those areas with energy markets like the Midwest ISO, both studying higher penetrations but lower costs. So you see these integration costs coming in on the order of $2 to $4, certainly under $5 a megawatt hour, under half a cent per kilowatt hour in those areas. And even in the other markets, you see it ranging maybe up to $10 a megawatt hour. But in both cases, pretty manageable costs. Another way to look at this is this just separates out on the left of those studies that are in hourly scheduling or areas without fast energy markets, and on the right are the fast energy markets. And this is showing the increase in reserves that's needed. So in this case of fast energy markets, we're seeing something on the order of 5 to 10% additional reserves needed. So it's not zero. There is impact for sure, but it's a manageable impact. And it's relatively well understood in these areas that have been studied. So again, the studies are showing that wind integration costs certainly less than $10 a megawatt hour and less than $5 a megawatt hour in many markets. Regulation impacts are small. a little bit larger impacts and load following unit commitment timeframes. Large balancing areas, intra-hour scheduling, use of wind forecasts can all ease integration challenges. And so just I want to finish with a couple of slides of summary, one on wind integration, one on flexibility, and then an overall one on integration of renewable energy. So as we look at this in whole, having large amounts of variable wind generation is relatively new. Our grids throughout this country and really throughout the world were originally designed around traditional forms of generation. They were designed around fossil fuels, nuclear, hydro. But variability and uncertainty have always been parts of those characteristics of those power systems. They've always had to be managed. This isn't a new thing with wind generation, but it's just an incremental additional amount. Wind and solar are variable and uncertain, and they do have impacts to the power system over varying time frames. These impacts are significantly reduced with large liquid fast markets, large balancing areas with a strong grid, and so that's a critical component, is to have a strong and robust transmission system, both within the grid footprint, the market footprint, but also with neighbors. And forecasting of wind generation significantly reduces that uncertainty piece of the variability and uncertainty. Power systems, we're learning, have a much greater ability to absorb variable renewable resources than commonly understood. So as we really look at the details, the technical details of how the grid works, we're finding that there is existing flexibility that can be accessed. And these points have been found in numerous peer-reviewed studies, including several here in the Midwest, that show that, again, it's effectively a balancing challenge. It's a tens of minutes to hours issue. We see here in the Midwest ISO that one of the new areas of development is what they call ramp management enhancement. So it's not an immediate need, but MISO is now developing their staff with stakeholders and members a product that they see coming into the market a couple of years out, where they explicitly provide a value on ramping resources. We've never had an explicit value on that. We value energy, we value capacity, we value ancillary services, but the ability of a generator to move, to ramp a certain megawatt per minute over a certain time frame is something that we need to start thinking more explicitly about. And we're seeing market structures starting to explicitly recognize that. Flexibility will be more and more a key and central concept in designing and developing and evolving our power system. And as we talked about, there are multiple sources of flexibility: dispatchable power plants, demand-side resources, grid interconnections, storage. And we not only need that flexibility, but we need to be able to access it. We need to make sure that that we have the market structures in place so that what's available is actually accessed and implemented. Key power system characteristics which affect how much of that technical flexibility we use include grid strength, market size, scheduling, dispatch, use forecasting, value of flexibility in the marketplace. As I said, market rules are starting to evolve, not just scheduling and dispatch, but market rules around the ancillary services. I just mentioned load following, ramp management. And we're increasingly to see markets where they're actually dispatching variable renewable generation. So wind generation is becoming part of the dispatch in the market rules, and that's a relatively new concept as well. So finally, just in summary overall, when you look at technical analysis, rigorous studies in whole, the finding is that large interconnected power systems can accommodate variable generation penetrations at levels not only up to, but actually exceeding 30% if we get both the infrastructure and the market rules right. So none of the studies that have been done have found a hard limit. There have been, many of those studies have been done in that 10 to 30% penetration, but there haven't been hard limits found there. In order to achieve these high levels of penetration, we need a robust and flexible transmission system. We need to keep that grid strong and interconnected, and we need to continue to develop market rules to operate and run that grid well. So thank you very much. I'd be happy to take any additional questions, comments you have, if you have any. Okay, thank you.